C8 Taylor series. Taylor series are so important that I'm going to review it here for you. I have other videos or two where I talk about Taylor series, but to keep it simple for you to have it all in one course, let's go ahead and look at this. We basically are looking at a power series for functions, and this goes back to the time of Newton and Leibniz in the 1600s that overlapped into the 1700s, the two mathematicians, and Newton's known for physics and math. They were independent architects of calculus. So to give you an example, we'll take e to the x. E to the x can be written as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. And we would like to be able to derive the series. That's what we're interested in doing. But even though these date back many years, like lots of things in physics and mathematics, we have developed simpler ways of teaching it with the benefit of having centuries of trying and investigating. So the way I'm going to show it to you is the modern method. And here you basically look at it, an arbitrary function, f of x, as a power series, say a naught, and that goes with an x to the 0th power, which is 1, and then a1. And here, actually, there's a more general form that has x minus a. Let's go ahead and do that. And then there's a second coefficient, and there's an x minus a squared, and so on, goes on and on. Now, when you pick a to be 0, now these coefficients, a's, have nothing to do with that a. These are the coefficients in front of the powers of x minus a. And you could think of the one here, x minus a to the 0th power. If you pick a to be 0, you then get the Maclaurin series. You can think of the Maclaurin series as a subset of the Taylor series. So then f of x would be a sub 0 plus a1x plus a2x squared plus, and you would go dot, 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 some a n x to the n plus, and keep going. Now we would like to write this in shorthand notation by saying we're going to sum. This is summation sign, summation symbol, where n goes from 0 to infinity, a sub n x to the nth power. So when n is 0, you get a sub 0, and x to the 0th power is 1. Then when n is 1, you have a1, x to the 1st power is 1. X, just going to be x. And then when n is 2, a sub 2, and then n is 2 is x squared, and so on. This n can be anything. Some people like to use k. So I like to think of this as, this is sculpting. This is like marble, and you want to sculpt it. You want to make the a's, you sculpt them so that you get something for the specific function in mind. So if the function is e to the x, then when you do your sculpting, you're going to get this. See? So how do we do that? Well, how do we shape the coefficients like a sculptor? Well, we notice that if we have f of 0, if we put in 0 for x, then we get a sub 0 because everything else goes away. And then we notice that if we take a derivative, say derivative, a sub 0 goes away, and then we pluck off the a1 here, and then the second one would be 2 a sub 2x using the power rule. And then here you would have n come down, a sub n, and then you would have x to the n minus 1. But now you notice that here, if you put in 0 for the derivative, everything goes away except a1. So in other words, the derivative, now this means take the derivative first, then put in 0 and see what you get. And what you get there is a1. Well, being encouraged here with derivatives, we'll take now the second derivative. Now the a1 goes away, and we pull off 2a2. And let's see, if we were to add one more in here, might not be a bad idea, a3 x cubed. Then here you would have pulled the 3 down, 3a3 x squared. So the next one would be here, you would pull the 2 down, you'd have 3 times 2, a3 x to the first power, and so on. So now you notice if you put in 0 for the second derivative, you pull off the a2 with the 2 in front because everything else goes away. Now it gets a little cumbersome to be putting all these primes up here, so what we will do is, for the notation here, we'll do the second derivative in parentheses like that. So therefore the third derivative would be, I put the 3 in parentheses. And if I take that and then put in 0, you can see I'm going to be pulling off, for the third derivative, I'm going to be pulling off this term. The third derivative, this goes away. And I'm going to have 3 times 2. I'm going to put a 1 in there. a3. So now we can see a pattern that's forming. If we look at this second case, this is a 2 times 1, a2, which is 2 factorial, a2, and this is 3 factorial, a3. And if you had, the fourth power, you bring a 4 down, and you keep getting these factorials. So what we're showing here is that if you take the nth derivative of the function and then put in 0, you're going to have n factorial times that nth coefficient. But that gives us the formula that we're looking for, because then the nth coefficient would be given by the nth derivative evaluated at x equals 0 divided by n factorial. So we can now write the general formula f of x with the summation symbol, n equals 0 to infinity, where we have a sub n, x to the n. We can now put in, for this a sub n, what this is. So if we do that, we would get the sum from n going from 0 to infinity of the nth derivative evaluated at 0 divided by n factorial, and then we don't want to forget the x to the n. So this is the formula. This is the formula that had to do the sculpting to get our results. Now some like to write it out. So if we do that, we would have, if you put n is equal to 0, you'd have here the 0th derivative, which is just the function. It's not taking derivative like this. And you would have x to the 0th power, which is 1. And 0 factorial, by definition, is 1. That's why that definition is made that way, to be consistent with things like this. And then we would have here plus the first derivative. I'm going to be a little cavalier and say, well, if I just have one derivative, I could just put the slash, but maybe I shouldn't. Just keep it consistent with the notation like this. And that's going to be divided by 1 factorial, which is 1, and x to the first power is x. Then the next one would be here the second derivative evaluated at 0, and this would be over 2 factorial, and this would be x squared, and so on. Now, the more general form of the series, the Taylor series, would be to write fx like this, where you replace the 0 by an a, and then you have the first derivative at a, and then you have x minus a. We have what we had set up before when we set up the general case, and then we would have here the second derivative evaluated at a, and x minus a squared over 2 factorial, and so on. The same derivative tricks would apply to our case where we had a sub 0 plus a1 x minus a plus a2 x minus a squared plus a3 x minus a cubed. Same trick would work. If I evaluate the function at a, I would get the first coefficient, all these go away. And then if I take a derivative, this goes away. And if I take a derivative here with respect to x, in other words here, saying first derivative with respect to x, this goes away. I would have here a1 by itself, because a1 times a is a constant, that would go away. And then for the next one here, I would bring the 2 down. Actually, I could do this by using the chain rule. I bring the 2 down, and I have the a2, and then I would have x minus a to the first power, but then I have to take the derivative of what's inside of here, which is going to be just 1, because the derivative of constant is 0, and dx is 1. And then here, I would bring the 3 down, a3, x minus a squared, and the derivative of what's inside of here is 1. So I'm just showing you specifically that the general case works with the same trick. Then here, if you were to look at the first derivative, you would get a1, everything else goes away. And then if you were to take another derivative, this would go away. And here you would simply pull off the 2a2, and then this would be 3 times 2, a3, x minus a, and more stuff. And then when you put in a for x, you would kill off everybody else and have 2a2. And then the third derivative would basically pull off this here. Now you can think of it that this times x, this gets pulled off, and then this times a constant, that constant's, that other piece is going to be 0. So that's going to be 3 times 2, a3. So here I still have things with x's in them, so what I have to go to the next step and evaluate where x is a, then all the other stuff goes away, and I get 3 times 2, a3. So using this kind of logic, the nth derivative, when evaluated at a, will be equal to n factorial times a sub n. A lot of times, the Maclaurin series works for us. But just so you know, in case, you have the more general case here, which is this formula. So most of the time, the Maclaurin series is going to be good for us, but you have the more general case here, which is this expression. When a is equal to 0, then you reduce to the Maclaurin. So there you have the introduction to the Taylor series and Maclaurin series, and now I'm going to do some examples in the next section.